Good morning, everyone. So, today we are going to discuss the last section of the module inclusion exclusion principle. So, it is about root polynomial. So, to understand, let us consider the problem of finding all arrangements of letters A, B, C, D, and E with some restrictions. So, the restriction is that there are some darkened squares. So, we cannot put A, B, C, D, or E in the darkened square. So, this is the restriction. For example, one of the permissible arrangement is you put A here, then you put B here, then C in 5, then D here and E here. So this is allowed because you can see that in each row and column there is only one letter. So this is allowed. So now we need to count the number of the permissible arrangements. So to count the number of the permissible arrangement, the first step is to define the universal set, and from where we compute n. So the universal set is the set of all, or is the all possible arrangements with no restrictions. So it means that the first letter has 5 possibilities, the second one has 4, and so on, and it means that it is 5 factorial. So it is set of all arrangement of 5 letters without restrictions. Now how do we define AI? So AI bar is, we cannot put the letter into the darkened squares. It means AI is ith position is the darkened square, and on the remaining position there is no restriction. It means that if I have defined A1 bar, then it is set of all collections of 5 squares, each in a different row and column. So collections of the 5 square, this is what need to be found, but with the condition that square in first column is not in darkened square. So we can deal with the either with the column or with the row, it doesn't matter. So I am just considering the column. Yes, it means if I have to define AI, then I will say set of all collections of 5 squares such that the square in column I is a darkened square. Yes, and this gives me, if I define AI bar and AI, then I need to compute n of A1 bar, A2 bar and A5 bar, because there are 5 letters. So let's start computing n of AI. So if I have to compute n of AI, then in the or n of A1, then I can see that in the first column there is only one darkened square. So there is only one possibility for A1, and for the remaining 4 there are 4 factorial possibilities. Yes. Similarly, if I compute n of A2, then again 1 cross 4 factorial. N of A3 is 2 cross 4 factorial, because there are 2 possibilities, and so on. So this is very easy to compute. Even you will observe that when you compute S1, which is summation n of AI, then it is nothing but all darkened squares. So S1 is 7 cross 4 factorial. So there are 7 darkened squares. Yes, so as I told you, to obtain Ni, we count the number of ways to put a forbidden letter in position I times 4 factorial ways to arrange the remaining 4 letters. Now next is to compute n of AiAj. So n of AiAj is little bit tricky. Why is it so? For example, if you compute n of A1, A2, then this is the possibility, only one possibility. But if you compute n of A2, A3, then you will see that you can put the letter B here, but if you put B here, then there is a problem, they are in the same row. It means you have to put the next letter C at this position only. So there are 3 forbidden square, but there is only one possibility in this forbidden square, because when we are putting it, we don't want same letter, or we don't want 2 letters in the same row or in the same column. It means that Nij is the number of way to put different letters in position I and j times 3 factorial. So when I have to put the different letters B and C, this is the only way I can put the two rows, and that's why it is 1. But if I see n of A3, A5, then you can see that I can choose this one and this one. I can choose this one and this one, this one, this one, this one, this one. So total 4 possibilities are there. So this is how it can be computed, and if you add them for S2, it is 16 plus 3 factorial. But you will realize that if I am doing this, then as the number increases, n of AI, AJ, AK and so on, there is a large computation. And when there are so many letters, then there would be too much of computation. It means we need a more simpler technique. Yes. So quick observation is S5 is 0 because in the 4th row there is no square. But S3, S4 you cannot compute so easily, and that's why we move to a next method. So this method, for this method we will consider the concept of rook. So rook is, in the chess game, it's an elephant, which if you recall, it moves horizontally and vertically. Yes. So it means that rook can capture any opponent's piece on the chessboard in the same row or column, provided there is no intervening pieces. So now the problem is to compute the number of ways to place k rooks on this board. We are talking of the board with the forbidden letter or the darkened squares. So to place k rooks on the board of darkened square is equivalent to our original problem. Why is it so? Because as I told you that when we put a letter in the darkened square, then in the same row and same column we do not want the other letter. Yes, so if it is a rook, then it's in the same row and same column, we don't want the other rook. So that's why, just to remember the concept, they have introduced the concept of the rook, otherwise the problem remains same. Now how do we solve it? That's more interesting. So we will introduce the concept of breaking down the given board into two disjoint boards. So let's see it, how it works. So the first operation is breaking down the boards into 2, 3, 4 disjoint boards. So something like this. You can see that this itself is a complete board. So if I can move this position to this side, so this will also come here, and then I can bring E here and I can put them down. So if I do this, then you can see that it get breaked into two disjoint board. Why disjoint? Because if you pick any rook here, then in the same row and same column there is no other rook. Similarly, if you put any rook here, then there is no rook. So this is one thing. Now what are the advantages? So the advantages are, for example, you computed AI AJ. Yes. Now in that case it was quite complex, but here you can see that for the board 1 there is only one possibility, these two processes, and for board 2 1, then next is this, and then this is, so there are 3 possibilities. So computation get very easy. To simplify it, we introduce some notations. So we say that RKB with the number of ways to place k non-capturing rooks on board B, and similarly you can define RKB1 and RKB2. So if you define so, then R1B1, so R1B1 there are only 3 possibilities, so it's 3, and R1B2 there are 4 possibilities, it's 4. If you move further, R2, so you have to place 2 rooks. So for this one only 1 possibility is there, and for this one there are 3 possibilities. But now how do you, now R3, now there is no way we can put 3 rooks because both the boards have only 2 rows. So RKB1 and RKB2 when k is greater than equal to 3 is 0. So this we have computed for B1, B2. How do we compute R1B, R2B? R1B is simple, we just add them 3 plus 4. But how do we compute R2B? Yes, it means putting two rooks on the board B. If you see this figure, then there are three possibilities for putting two rooks on board B. Either you put two on board B1, two on board B2, one on board B1 and one on board B2. So this gives you R2B as R2B1 plus R1B1 R1B2 plus R2B2. Yes. Now just for the convenience, we always assume R node B or R node Bi is always equal to 1. So R naught is always equal to 1 irrespective of any board. So because of this, I can write down R2B as R2B1 R naught B2 plus R1B1 R1B2 and so on. And this number comes out to be 16, which we have already computed when we are computing S2. Yes. So this is the generalized lemma. If I have to compute RKB and if there are two boards B1, B2, then it is RKB1 R0 B2 plus RK minus 1 B1 R1 B2 and so on, and in the last R0 B1 RKB2. And this makes sense because you are just, if there are two boards, you are combining all possible ways. So if there are 5 there, then 0 here, then 4, 1, 3, 2, 2, 3. So all possible combinations we are considering. The next concept is Rook polynomial. So Rxb is defined as R0b plus R1bx plus R2b x square and so on. Yes. So now let's compute Rxb1. So if you remember it, then R0 is 1. Then R1 you computed, 3 possibilities are there. So 3x and only one possibility for R2b1. Similarly Rx, so 1 plus 4x plus 3x square. Now from here, how do we compute Rxb? Yes. So Rxb, again, what we are looking for? We are looking for the different coefficients of x. So if I need the coefficient of x raised to the power k, then I multiply Rxb1 and Rxb2 and look for the coefficient of x raised to the power k. Same we did in the generating function. It means Rxb is simply the multiplication of Rxb1 and Rxb2. So if you multiply it, then Rxb looks like this one, which is your required Rook polynomial. So actually you are looking for the Rook polynomial because these terms will give you the required R1b, R2b and so on, and using this you can use the inclusion exclusion principle. So n of a1 bar, a2 bar and a5 bar would be this one, where s1 is r1b 4 factorial, r2b 3 factorial, r3b 2 factorial and so on. Yes, and the values of r1, r2, r3, everything comes from the Rook polynomial. It means the number of ways to arrange n distinct objects with restricted positions is n factorial. If you have to arrange n objects, minus r1 n minus 1 factorial and so on, where rk are the coefficient of Rook polynomials Rxb for the board of forbidden positions. So you can see that very interesting mathematics. We have transformed very difficult problem into a very simple problem. So this is what we have done. We have given a problem. We need to count the number of permissible arrangements. For this, I first transform it into the disjoint boards B1, B2. Then I compute Rxb1, Rxb2. Then multiply them to get Rxb, and then use Rxb to have the required answer. So that's all from today's class. In the next class, we will see different questions and also see the case when it is not possible to break into the two boards, and if there are more than two boards, how to handle those cases. Thank you very much.